optimization for vertical axis wind turbines designed using independent CFD tools. Again, this recording will be available as well as some of the scripts that we used during the presentation. I'd like to start by introducing our presenters today. We're joined by Chris Sideroff. Good morning, Chris.
Morning, Drew.
Morning. Now, Chris has been with Pointwise since 2007. Before that, he had a stint as a petroleum engineer. Chris did his undergraduate and master's work at the University of Alberta before receiving his PhD from the University, or Syracuse University in 2009. And where he spent most of his time looking at microenvironment CFD. And we're also joined this morning by Travis Kerrigan. Good morning, Travis.
Good morning.
Now, Travis worked as an intern at Pointwise since 2008, and he's been working with Chris, and he's completed his master's in aerospace engineering, and today we're fortunate enough to have Travis talk about some of the work he did while he was at the University of Texas at Arlington, where he looked at aerodynamic shape optimization of vertical axis wind turbines. Good morning, Travis. My name is Darrell Rittenberg. I'm the Director of Customer Development here at TechBot Incorporated. We're your host today. My background's in chemical physics. I have my PhD from the University of Utah, where I also did a stint of research at the University of Osaka. And with that, let's go ahead and look at our agenda this morning. So we're going to start with a quick overview of some of the motivations for this study. And then we'll look at the problem setup, and we'll have an opportunity to look at some of the methodologies for automating the grid generation. We'll have an opportunity to discuss the results of the study, as well as an overview of looking at the system and how do we get to the optimal design. So just a quick, to put this in context, there's been a fair amount of research recently in moving from the macro to micro power generation. Now, in the United States, that's perhaps relevant, but if you move to the developing world, we're looking for many ways to have small organizations or small ways of bringing power. Now, this is, of course, a green technology, so we're looking primarily at wind and solar. And this is, of course, in the domestic market, we're interested in lowering our carbon footprint. Now, with gas prices continuing to rise and fuel consumption continues to rise around the world, we're looking for alternative ways. And this particular area is very well funded at this point. I know Obama has set aside a significant amount of money to look at some of these technologies. So that's kind of some of the backdrop of why this is an area where there's so much interest. With that, what I'd like to do now is turn it over to Travis, and he's going to talk about one study where he was optimizing a vertical wind axis turbine. Travis.
Thanks, Darrell. So there's two major types of wind turbines. There's the horizontal axis wind turbine, and when I talk about these are generally larger with rotor diameters in excess of 100 meters. They produce more than a megawatt of power. Then there's the vertical axis wind turbine, and when I talk about the vertical axis wind turbine, I'm talking about those that are generally smaller, placed in urban or suburban areas with power output of just a few kilowatts. So there's a little animation in the bottom there just showing the different types of wind turbines. So narrowing it down a little bit further, looking at the vertical axis wind turbine, it's really a personal green energy solution. It's really a way to bring energy right to where it's needed. They're very small, quiet, relatively easy to install. They can operate in a wide range of wind conditions. One of the major benefits is they can take wind from any direction because they rotate about an axis that's perpendicular to the wind. They don't have to be yawing into the wind. And they operate very well in fluctuating turbulent wind conditions that are generally found around buildings in urban areas. So there's two types of vertical axis wind turbines. There's the Darius and the Savonius. And the Darius will produce torque through lift. I'm going to talk a little bit more about them on the next slide. And the Savonius produce torque through drag by capturing air and blades that resemble a bucket shape. There's even a hybrid type, as you can see in the lower right-hand corner. That's really just a combination of these two types of rotors. Narrowing it down just a little bit further, this is the Darius vertical axis wind turbine. Like I mentioned earlier, it's driven by lift rather than drag like the Savonius rotor. The reason for choosing a Darius type wind turbine over the Savonius for the optimization is that a Savonius rotor is generally limited to a tip speed ratio of around 1, meaning that it'll rotate at roughly the same speed as the oncoming wind. Whereas the Darius rotor, being driven by lift, can actually rotate a little bit faster than the oncoming wind. In other words, with a tip-speed ratio greater than 1, effectively increasing its efficiency. So to kind of give you an idea how a Darius type rotor operates, you can see the schematic there. The blades rotate about an axis that's perpendicular to the wind, and each blade is at some angle of attack to the relative wind, and this angle of attack will change with the blades' azimuthal locations around the wind turbine. And we know that a blade at an angle of attack to the relative wind will produce both a lift and a drag component, which we can break into this normal force component that points into the center of rotation, not really contributing to the torque, and a tangential force component that's really the driving force of the wind turbine. And it's this tangential force component that's actually used to determine the torque of the wind turbine. So the real motivation for this project was to maximize the efficiency of the wind turbine by allowing the blade shape to change as the optimization progressed. I wanted to minimize designer experience or intuition because there's actually quite a large community designing and building these wind turbines in their backyard or garage. They don't really have a lot of experience in this area. So by minimizing the amount of user input, someone without a lot of experience could actually get an improved design for a very specific operating condition. Also, reducing the design cycle time frame by using an automated computational framework really reduces the cost by eliminating the need to spend countless hours like manually constructing many physical or computational models and analyzing each one individually through some sort of design of experiments or exhaustive search technique. Another thing is I wanted to incorporate some independent analysis tools. Rather than using a single package to run through the entire optimization loop, I wanted the freedom to pick the best tools for a given task while also being flexible and having the ability to work well with the other tools that I chose. So looking at the tool selection specifically, you can see here's the optimization loop or methodology for this problem. And included is a very typical analysis workflow from geometry generation through post-processing with a closed loop to accommodate the optimization algorithm. So the important thing to note is that I've chosen to break the process up into what I call analysis modules, giving me complete control over the individual tasks as well as the entire process. So what this allowed me to do is essentially plug in a specific tool for a certain task, ultimately giving me the option to choose the best tools for the job. So the tools I chose had to be flexible with robust I/O capabilities, as well as have good scripting capabilities, so I could run the entire process in batch mode, without constantly asking the user for input. A good way to put it is that these tools had to be plug and play. Just plug in the tool and start using it right away without any compatibility issues. So I ended up choosing Pointwise to generate the grids I'd be using, Fluent as a solver, and TechPlot for post-processing. But again, it's important for me to note that because this is a modular process, I really could have picked any tool, but these individual packages met my needs. So now I'm going to pass it over to Chris, who's going to discuss how Pointwise played a role in the optimization routine and demonstrate an interactive script I wrote to automatically generate grids for the various geometries analyzed throughout the optimization. So Chris?
Okay, well, for Travis's work, Pointwise was used for both geometry creation and mesh generation. It was Pointwise's scripting language that we call Glyph, kind of what tied this all together. And Glyph is built on top of Tickle. It's an open, well-documented, very mature dynamic programming language. And Glyph is essentially just a suite of Tickle functions that give the user access to all of Pointwise's capabilities. Also included with Tickle is the GUI toolkit called TK. And this essentially allows you to write your own customized GUI interfaces. So I'm just going to show you all this in action. So here I'm in the main Pointwise interface, and I'm actually going to open up the GUI version of the script that Travis used for the optimization process. So the script can be broken down into 3 sections. We have a geometry creation section, we have a boundary layer mesh generation section, and then we also have a far field mesh generation section. So I'm just going to go ahead and create the geometry first. So coded up into the script is the NACA4 series equation. In the interface, I can only enter integer values for the equation, but in practice, this restriction isn't necessary, and you'll see later on in some of Travis's results that the optimized airflow actually has non-integer values. This is probably just a good opportunity just to show you the nature of a Glyph script. Hey, Darrell, I'm going to get Darrell to go ahead and just open up that Glyph script in the text editor for me. Thanks, Darrell. I'm just going to move down here to maybe just in a little different part of the script itself. So here's a good part to look at. So this is actually this for loop here. We have a for each loop. This is just a typical for each loop. And so we can see the equations for the actual NACA 4 series equations. We have the equations for the camber line, and we have the equations for the thickness. And at this point, this is all just pure tickle. And if I just go down here a little bit further, we can see an actual call to pointwise through a glyph function. And typically, they just start with a PW colon colon. And just the last quick comment about glyph. It's fully documented, and then there's a tutorial manual provided with the software, so it's pretty easy to get up to speed. And tickle is a fairly easy to learn language. So just getting back to the interface, I'll just bring up the script again. So having the ability to create the geometry is probably the most flexible and robust approach for automating mesh generation. And actually, Pointwise has quite a few tools for creating geometry. And that's the create menu that contains these types. So I'm just going to get out of the script for a second just to show you some of these tools I was just mentioning. So if we go to the create menu, and we can see here there's just a kind of a nice little list of geometry creation tools. We can create revolved surfaces and swept surfaces. We can create fillets. An interpolated surface is just a basic ruled surface. Kuhn's patch is a type of three-dimensional NURB surface, as well as a whole host of curve drawing tools. But I'm not going to profess that Pointwise can completely replace a full-featured CAD package, but it does have enough tools to get the job done for geometries of a reasonable complexity. This isn't the only way it can be done. You could also import files containing a series of points from which you could generate some curves and surfaces, or you can even import a complete geometry from a third-party CAD software. And it's your choice. You just pick whatever suits your needs the best. At this point, the most straightforward way to get external CAD data in is using the IGES format, and Pointwise supports a few others, such as STL, Vermo, and a few other discrete formats. The ability to import native CAD formats, ProE, SolidWorks, CATIA, just to name a few, will be coming in the next major release of Pointwise a little later this year. I'm just going to get back to the script again. So I'm going to go ahead and create the mesh. So I'm going to go ahead and create the boundary layer portion of the mesh. And you can see that the boundary layer meshing region is driven by typical boundary layer parameters. We have the initial cell height, we have the growth rate, the total boundary layer height, and then also the number of points around the arc to control the resolution. So in this case here, it's gone ahead and created a structured extrusion around the 3 blades, because we specified a total of 3 blades with a solidity of 1.5. And then for the far field, there's a variety of parameters that drive that. So I'm just going to go ahead and create that and then describe what those parameters mean. So we have 2 for the rotational part and 2 for the far field part. So I should stop and just mention at this point that all the trapezoid simulations run steady. The blades rotate in an inner zone that physically move, and then there's another portion that's stationary. So this is just a sliding mesh simulation that handles pretty seamlessly. So in the far field mesh generation portion, we can control the size of the rotational domain as well as the number of points around the circumference, and the same for the far field. So before we move on, I just want to talk a little bit about the topology that Travis chose. So if we again zoom in, we look a little closer again, it's pretty obvious that this is a hybrid mesh where we have a very high quality structured mesh around the blades. Then we have a hybrid mesh, an unstructured mesh, excuse me, in the far field. So a very subtle but yet important piece of Travis's work included a mesh dependency study where he investigated not only different mesh resolutions but also different mesh types. So since it was a relatively straightforward geometry, he initially thought that a fully structured mesh would give the most accurate and reliable results. For his application, he discovered this wasn't necessarily the case. He found the solution that was most sensitive to the boundary layer and not the far field mesh. And so surprisingly, he found the hybrid approach actually gave a similar answer to the structured mesh with the benefit of a reduction in the number of cells. And if we just back up to the previous slide, we can see why. So for the structured mesh, the high resolution near the blades is unnecessarily propagated into the far field, and this doesn't happen with the hybrid approach. So for optimization, the savings in the number of cells is actually very important. So even though that Travis's work was just 2D, which on today's computers can be run relatively quickly, just for a single case, it's the fact that the simulation is unsteady. So for stability requirements, we know that the time step size is driven by the CFL, or also known as the current number. So therefore, as we decrease our cell size, we also have to decrease our time step size for stability reasons. So for unsteady simulations, having the grid size increases the runtime not by a factor of 2, but probably closer to a factor of 4. So we can see here that on this simplified plot, as mesh size goes up, the runtime for an unsteady simulation increases quadratically, whereas for a steady simulation is probably somewhere around linear. Now, of course, this wouldn't be a problem if Travis were only running one simulation, but he actually ran several hundred simulations, so very significant a benefit to doing that. So another benefit of the hybrid approach is that it's easy to automate the meshing. The reason this is important is that reliable and robust automated meshing is an absolute must for optimization. The optimization can create hundreds or even thousands of meshes with a wide and often unknown range of geometry types. And Travis has stated several times that PointWise's ability to seamlessly create hybrid meshes provided the high level of reliability that was demanded by its optimization process. So he ultimately settled on the medium resolution mesh. The boundary layer resolution for this case resulted in a Y plus of 1 or less than 1, so all functions didn't have to be used. So at this point, I'm going to pass it back to Travis, and he's going to talk a little bit about some of the results from a very specific case.
Thanks, Chris. All right, so the optimization algorithm chosen for this study was an in-house differential evolution algorithm. It's a stochastic direct search method where the parameters, mainly the airfoil parameters, are represented by floating point values like Chris mentioned rather than binary strings like in some evolutionary algorithms. And it doesn't require the problem to be differentiable or continuous as is required by local gradient-based methods. And this makes it attractive for design optimization where the characteristics of the solution space may not necessarily be known beforehand. It's also very fast because each objective of function evaluation can be done in parallel. It's robust and simple to use with just a few user-defined parameters. The design parameters are generated through mutation, crossover, and selection operations, and this is very typical of an evolutionary type algorithm. So in this case, the objective function, or cost function as it's often referred to as, is just the average torque for a single rotation of the wind turbine, where the design parameters are just the 3 parameters for the NACA 4 series airfoil, the maximum thickness, maximum camber, and maximum camber location. The first test case was just a proof of concept test case for a high solidity of 1.5 and tip speed ratio of 1. There were 14 parents or candidate solutions in each population, and the optimization was run for 11 generations on our cluster, and this gave it a runtime of about a week. And this is long enough to obtain an improved design. The optimization was considered successful if the wind turbine performed better than the baseline. In this case, the baseline was chosen as the NACA 0015 geometry, which is a very popular geometry for these types of rotors. Now, I should stress, though, that in optimization, the idea is to find an improved design, not necessarily an optimum, as the only real way to guarantee the design is optimum would be to do an exhaustive search, which in most cases is pretty much unrealistic. So here you can see the optimized geometry compared with the baseline airfoil. The optimized design is a little bit thicker than the NACA 0015, 15% airfoil. The optimized design is roughly 18% thick, and it's got some slight aft camber. But in the end, this is what we're looking for. The optimized geometry performs 7% higher than the baseline geometry at the design tip speed ratio of 1, which is a significant improvement for a device that's operating almost continuously in the right conditions. Now, in order to understand the mechanism for improved efficiency over the baseline geometry, I'm going to pass it over to Darrell to discuss how TechPlot was used to visualize the unsteady flow field and reveal some interesting flow field phenomena observed for this high solidity rotor. So, Darrell?
Thank you, Travis. Okay, well, one of the things that we want to discuss or think about at this point is that we know that the system went through and there was an optimization. We want to understand what the mechanism of that optimization is. So we want to use post-processing to evaluate the process, really try to understand what's behind that optimal design. And finally, how are we going to present that information? So when we think about how we might present that to someone who would be building this, we want to show them, hey, this is how we came up with this design. This is why the Savonius, if we were looking at more of a, if we're looking at a Savonius versus a Darius wind turbine, we're going to look at how we got to that optimal design. So first, I think it's probably best to just start with a static image. Now we're looking at 3 generations. This is the initial design and the optimal design. We're looking at 3 intermediate designs. And one of the key things that comes out of this analysis is you can see that there's some vortex shedding off the leading edge of the airfoil. And that's leading to additional drag. Now again, that's we're not trying to optimize drag in this context. We're trying to optimize lift. Now if we look over here at just the average lift on the blade, or the average pressure on the blade as it goes through the rotation, this red line represents the optimal design, whereas the blue line represents the initial design. And you can see that there's about a 7% difference quantitatively. Now this is an unsteady phenomenon, so ultimately we're going to need to look at this in the context of an animation. So what we're looking at here is the optimal design candidate versus the original design candidate. And you can see the NACA 15 airfoil. You can see that we have that formation. I'm going to use the animation slider here. We're going to go back so you can see this in more detail. So you can see in this area where we've actually shifted that vortex shedding to the trailing edge of the airfoil. And at the same time, if we look at the quantitative pressures on those airfoils, and we look in particular at the values here, they range from a value here, which this is the same 20, and here's 20. You can see that the maximums here are about, again, about 7% over the initial design. So you can see that we can present kind of a simple image. If we wanted to dive in a little detail, we can actually open these data in TechPlot. Now, to point out, everything I've shown you up to this point can be done in an automated way. TechPlot's completely scriptable, and one can actually launch TechPlot to intercept the fluent files as they come off the simulator and process them. And we've actually done some work, which I won't actually open up the script, where one can actually do this in situ. So as the fluent is actually going through its simulation, as each individual case and DAP file become available, TechPlot will recognize that there's an available file, process that file, either generate an image or add it to something that we call a lightweight export. It's not truly important. So what I have here, again, are the optimal design, and we're looking at the original and optimal design. We're looking at those pressures here. Now, again, to quantify those data, let us quickly just take a look at the maximum here. So we're looking at a value of about 24 for the optimal design versus a value of about 23. That's for the initial design. So again, about that 7%. Now we have, these data are transient, and if I move back and look at the one blade in a little more detail, so that you can really appreciate that fine structure here. So what we're looking at, you can see here we have that vortex shedding right off that leading edge. Now this is, as you can see, because the number of contour levels in this area aren't all that fine, it may be difficult to understand what's going on. One of the things that people often want to do is to evaluate the fine structure by adding in additional contour levels to really try to understand more about what the shape of that shedding looks like. And we can add those interactively. Again, that just gives us an opportunity to identify that fine structure. Additionally, we may want to take a look at these data as they animate and be able to do that on the fly as well. So if I just walk over, we can actually play through now. So we can watch that, and we can at the same time watch how it's the quantified values as well. Now if I pause here, you'll see that, I'm going to redraw this real quick. You can see that at any particular time I could move back and forth. Now when I want to present this information out to say a presentation or put it in PowerPoint, we can very quickly just dump this off into a file if we chose. Now you can use a number of different formats ranging from your flash file to the Windows Media video. So really, you have an opportunity to present the information or put it in a file format that works well for your audience. So if you're working with people primarily in Windows, you may actually choose the Windows Media file. The other thing to point out is that although these data were in Fluent, in principle, the same kind of analysis could be done with data from a number of different sources. So they range from your typical finite element codes like ANSYS, Abacus, and Nastran. Fluent, of course. We also have the more general CGNS, Plot3D interfaces as well as Kiva. So although the analysis we chose to do was aerodynamic, there are a lot of people who are using similar unsteady analysis to optimize things like pressure on or and/or temperature, looking for optimal heating rates. And so in that case, you can actually think of doing a very heterogeneous environment where you may actually look at a coupled solution, and you'd have the ability to do that within this interface as well. So with that, hopefully you get an understanding, or you can see how one might present the information. And ultimately, you may just want to take this right into PowerPoint. We could just take this right off the clipboard as a bitmap image, just take all the frames here, and if we did, we could put them into PowerPoint, or if I wanted to put them in here, it's not overly important, but we could just drop it right in. But I'm going to dump back into PowerPoint. I want to make sure we have plenty of an opportunity to answer some questions here. So let's see here. Let's get back. So let's just talk about two things. We do have a tutorial where we'll dive into a little more detail on strategies for working with unsteady CFD results. That'll be Thursday, May 12th. If you're interested, we'll send out some links to that, and they'll be available on our website. So just to summarize, we've shown how one can actually leverage the best tools available to use for CFD optimization. Now, we chose, in this case, Pointwise, Fluent, and TechPlot, of course. But you really could use any tool. That includes, there was a couple of questions that have come through already on OpenFOAM. Of course, the same strategy would work with OpenFOAM. It would work for CFX. It would work for STAR CCM. So you really have quite a bit of flexibility in selection of tools for a given study. And that's kind of the key thing here, is that depending on the system you're looking at, you may want to choose a simulator that's better for a particular flow regime. And with that, what we'd like to do now is open it up to questions. We do have some that have already been typed in. Again, just to remind the audience, if you are interested in asking a question, there's two ways to do that. One, you can raise your hand. If you raise your hand, we can select you. We'll unmute you. You can ask the question, and Travis, Chris, and myself will try to answer that. The other way that you can do that is if you go over on the control panel, you can type in a question in the questions dialog, and we'll answer those as well. So I'm going to start with some of the questions that have already come in. Again, if you've got a question, please go ahead and raise your hand. But let's start. The first question was, could you talk about which optimization framework was used for this analysis? Travis, I suspect that's for you.
Could you repeat the question real quick, Darrell?
Yeah, Olaf Froman is asking, could you please tell which optimization framework you were using?
I'm assuming he's talking about the algorithm. So in that case, it was the differential evolution algorithm.
Okay. All right. The second question was for Chris. Chris, there was a question about trying to quantify some of the numbers on that graph where we were looking at time savings, especially for unsteady. If perhaps you could give some flavor for what those relative savings are.
Well, basically what I was just trying to point out on that graph, if you want to navigate back to that plot for me, Darrell, basically what I was just trying to point out is that there's the actual runtime that's required for an unsteady versus a steady. As you increase in mesh size, the rate of change is a lot different for an unsteady versus steady, because like I mentioned, the time step size is typically driven by the CFL number, which is U delta T over delta X. So as you have delta X to maintain that current number stability, you need to have delta T. So not only is for a steady case where you're not worried, you're just advancing in some pseudo time or just using some relaxation to. So basically, as you have your grid size in a rough sense, you just double your runtime as you double your mesh size. But for an unsteady, you not only double the mesh size, but you also now need a time step size that's half the size. So like I said, the runtime it goes quadratic or unsteady. So that's kind of what I'm just pointing out here. So even though Travis's case was 2D, because it was unsteady, it was very important that he tried to keep his cell count down so that, again, because he was running hundreds of simulations, and I think I don't know if he'd mentioned or not, but I think he said for one optimization case, I think it took him a week with the 50,000 cell unsteady case. So you can imagine, as you have the mesh size, now that's 4 times as long, so now it takes 4 weeks for one case.
There's a question from Michael Lawson, who is asking about said that the tip speed ratio seemed low. Typically, the TSR for vertical axis wind turbines is about 5 to 7. Travis, do you have a comment on that?
Yeah, it was low. This first test case was just a proof of concept. Simply just take a high solidity rotor, in this case 1.5, a low tip speed ratio, and run it through. Truth is, I actually have more data for a higher tip speed ratio case, where I also did the same optimization for that too. But this was just a proof of concept test case. And this is all going to be published in a journal paper. It's pending publication right now, so you'll be able to see that data as well soon.
Robert Gordon had a question. Would he be able to have access to your script? He'd also learn how you could use this optimization perhaps even with OpenFOAM rather than with Fluent.
Okay, yeah, I'll get this one.
Sure.
The script will be available. It can, like Chris mentioned, it can be run in batch. You can strip the GUI out and run it in batch mode from the command line. And right now the script doesn't export to any solver, but Pointwise does export to OpenFOAM, so you can take this script and actually use it with OpenFOAM as well.
Okay. Let's see, just want to put this back very quickly on the question so that if someone has a question they don't want to ask here, that at least they know where to pose those questions. Going back to that optimization loop, Doug McCorkle would like to know what tool you used for the optimization code itself.
Yeah, like I mentioned earlier, the optimization algorithm itself was the differential evolution algorithm. It's just an in-house code that we have in our lab, so we can do all the function evaluations in parallel and then feed it to this code, and it'll go through the generations and everything. So that's what we used in this case.
Okay. Someone had asked whether or not you had, and we don't have access to, so there's Rongling Chen who is asking whether or not we have the mathematics for the model available that we could show on a slide, and I don't believe we do. But we can circle back with you and at least give that to you. There's a question about compatibility with TechPlot. This one's more for me, I guess, with ANSYS CFX. Typically, what we're seeing is people are using the CGNS export from ANSYS as the primary way to bring data from the CFX code into TechPlot. So that's just a question there. Whoa. Sorry. Let's bring that back up. Too many mouse clicks here. Okay, we do have a few more questions here. Let's see. Karis Hamid is asking, I've done some optimization using Fluent, and I get a NACA 22 airfoil as optimized airfoil, but that was in 2D using a sliding mesh technique. Will the results change when I go to 3D? That's a good question.
Yeah, in 3D, that's basically just this case extruded. So if you assume that you're extruding it really far, very high aspect ratio blades, right? The tip leakage would actually have a little bit of effect, but not too much. So you could imagine if you were to extrude this with a high aspect ratio, you could get pretty much the same results. I'm assuming that the performance you get will be a little bit different, but the overall idea, if you optimize in 2D, it might actually work in 3D. That is a question that I have to answer by doing a little bit more research and actually taking it into 3D.
Okay. Travis, just to continue on that, there was at least 2 questions on that. So there was a question of, you tried to look at the 3D simulation or the 3D behavior?
No, I have not tried looking at the 3D behavior yet, but that has been marked for future research most definitely. So.
Okay, there was a question. Can you comment on the sliding mesh used for the calculation?
Yeah, I'm not sure if it's probably not best. It's probably best for us, not appropriate. I'm not really sure what direction the question they want us.
Okay.
How they want us to answer, but it's probably best just to contact your ANSYS rep. I'm probably guessing they're concerned about quality issues at the interface, but you can see in Travis's case, he kept the interface a long ways away from the blade. So if that's where the direction of that question was going, but the best is probably to talk to your ANSYS rep and get the best. He'll probably give you the best feedback on that.
Okay. There was a couple of questions around where will this work be published, Travis?
Right now, that's uncertain. I'm not going to mention anything about that yet, but it is publication pending. So, but as soon as it's published, we'll put it up online, so it'll be available on our website.
So there's a couple of questions about what release of TechPlot I'm using. I'm actually using TechPlot 360 2011, which was released last week. The primary thing that we've added in this most current release is better support for unsteady simulation. We'll have a follow-on webinar where we'll talk about that in more detail. So I don't want to use this as an opportunity, but do look forward for that. We will have more practical strategies for looking at unsteady results at that time. There was a question, let's see here, around is pointwise structured mesh possible or not? The question.
Yes, absolutely. That's the bread and butter of pointwise, our meshing algorithms, and you've seen it in action around the blades. That was a hyperbolic structured extrusion from the blades, and then we filled in Travis filled in the rest with an unstructured. But I think there was one slide where I showed also a fully structured mesh. So it has true fully structured meshing as well as unstructured and some hybrid, and they can be all combined and work together all in the single interface.
There's actually two questions that are interesting. The first question was around what was shown in terms of the contour variable. That was just vorticity. So you're looking at the vorticity around the airfoil. The second question, which is actually kind of an interesting one, was more about can you be sure that the dampening of the vortex on the leading edge was due to the optimization and not a change in mesh? And are you sure that the Y plus was maintained? Good question.
That's a pretty good question. It requires some further investigation. So if you'd like, you could get in contact with us after the webinar, and we could talk about it a little bit more.
Okay. So there was a question about some of the time-aware capabilities in TechPlot, specifically around being able to show a time marker on screen in the XY line plot. Yes, we now have the capability where you actually can look at time and have time develop so you can have a time marker. So that's, again, TechPlot, the release that happened last week has that capability. What turbulence model was used? Sam Rowland is asking that. Travis?
The turbulence model in this case was just the Splart-Almaris one-equation turbulence model in Fluent.
Okay. There was a question about CP looked very high for a given tip speed. Doesn't one expect a CP value at around tip speed of a ratio of 4 to 5? Travis, I suspect that's for you, although I don't know if we didn't plot CP per se. So I guess I'm not sure we can answer that question.
Yeah, I don't think we can answer that question.
Are all the analysis done in Fluent? Meshing optimization, post-processing running in one machine or in several machines?
They were done in Fluent. The solutions were done in Fluent, and it was done on a cluster, so it was done across several machines.
Now, someone's asking whether or not you've extended your analysis to look at farms of vertical axis wind turbines in urban areas, for example. Is that something that you're doing or considering doing? Travis?
Oh. No, haven't extended this beyond just looking at one single vertical axis wind turbine.
Okay. Chris, this is probably, perhaps for you, how can you be sure that the solution is mesh independent using the optimization method?
How can the solution be? Well, like we showed on the chart, I mean, Travis had, performed a mesh independency study where I think the highest resolution mesh, I'm not sure if he showed it on there, I think the highest resolution mesh he did in 2D was actually 500,000. I think I showed on the chart earlier in the presentation that there was, I think the finest was 100,000, but he went up to 500,000 in 2D, and there was no change. And so for his purposes, he was interested in looking at torque, which is, I realize is just an integrated value. So he was just looking at the influence of mesh resolution as well as mesh type on the actual torque itself. And so the histogram I showed earlier was looking at that. So there was one data point that wasn't shown on, would have been on the far right, which would have been 500,000, but essentially the torque was unchanged from 50,000 to 100,000 to 500,000. So I guess Travis is pretty confident that he felt that that was, at least for the purpose of this study, was deemed mesh independent or sufficient for what he was looking for.
Okay. Quick question: what was the Reynolds number based on tip speed? And that's a question.
That's a good question, and I'll have to get back to you on that. You can contact me. The Reynolds number does change. I was calculating Reynolds number for the airfoils, and it changes as they rotate around. So yeah, you can contact me, and we can talk about that.
Okay. Chris, there's a question for you on how difficult and/or easy would it be to do systematic grid refinement with pointwise?
Well, for structured meshes, it's really easy. That's no problem. I'm assuming by systematic he means like a halving or a doubling, finer or coarser. Now for unstructured, it's a little trickier because you essentially just feed it the boundary points and it automatically generates the mesh now. So no problem for structured. A little bit more difficult for unstructured. You would have to do it some other manner, but so. Again, that's probably a good question that we can talk about or I can answer offline. These questions come up quite frequently.
Travis, another question for you. In your study, did you validate the baseline case before moving to the optimization?
I validated it in the sense that I compared the trend with the trend of a similar wind turbine. Because this was done in 2D, I couldn't really validate a 2D wind turbine. So I just simply compared the trend, and the trends were almost identical in terms that there is an optimized or an optimum tip speed ratio, and as you move away from that, the coefficient of performance drops off on either side. So that's the validation I did for this case. Now going into 3D, yes, that would be one thing to do, would be to actually take the baseline and compare it with an actual three-dimensional wind turbine to validate it. But in this case, I was just looking at the trend. Again, this was like a proof of concept study, and there's further research down the road, most definitely.
Okay. Two quick questions. There's been a number of questions about how do I contact whom. The best way to contact either TechPlot or Pointwise, and that would include Travis and Chris at Pointwise and myself or one of my support engineers here at TechPlot, would be either at support@techplot.com or support@Pointwise. So if you want to go ahead and contact Travis, that's probably the easiest way to get a conversation started. Let's see. Why SA model was used. It is only a single equation model, not a RNG model with K epsilon. This is, I suspect, another one of the. There's been Harris Hamid has got several questions. I think he would like to perhaps take some of those questions offline. I think we have time for just a few more questions. I haven't seen anyone raise your hand. Oh, wait a minute, never mind. Hold on. We have one hand raised here, and I'll see if I can add that person to our discussion. There it is. So I'm going to unmute you here 1 second. Okay. So this is Khalid, and Khalid, you are unmuted. Unmuted. So Khalid, Ali Mohammadi, if you have a question, you can go ahead and ask it at this time. Well, let's see if maybe it's better if you just type that in. Let's see. Did you set up a rotational speed, or did you evaluate it from the estimation of the resistance from the elastic system attached to the wind turbine?
No, I set up the rotation speed. So I just gave it a fixed tip speed ratio. I fixed the inlet velocity and the rotation speed of the wind turbine.
Okay. We have time for just a couple more questions. It looks like we have a question from Udit Goyal. Udit, I'm going to go ahead and unmute you. So if you have a question, please feel free to ask it at this time.
Hi. Actually, I typed in a question before. I was referring to a plot where you had the coefficient of performance plotted against the tip speed ratio. You correctly said that the trends of the CP look the same, that there's an optimum at a particular tip speed ratio, which tends to fall on either sides. But I mean, what I thought was that at tip speed ratios of 1, these Daria wind turbines kind of give very low coefficient of performances. Is the value of 0.4 at tip speed ratio 1 looked kind of something that I would not expect. Any comments?
Yeah. Again, this was an optimization. So we were optimizing for that tip speed ratio. So it's not entirely certain that it is uncommon that you could get an efficiency that high if you were optimizing the blade shape. But again, yes, I've seen similar things in literature, and this is why going into 3D and actually analyzing the performance of these high solidity rotors at these low tip speed ratios would probably produce more accurate coefficient of performance. But again, the trend is what I was shooting for, and the trend is very similar to not necessarily the absolutes of the trend, meaning coefficient of performance, but the actual shape of the curve very much the same with a real vertical axis wind turbine. And that's what I was looking for, just to make sure that I was getting the same trend before continuing on with the optimization.
Okay, thanks.
Thank you. Let's see, we have another question from Fareed. Hold on one second here. Okay, yes, Farouk Saeed. Farouk, we're going to go ahead and unmute you now. If you have a question, feel free to answer or ask it at this time.
Hello, can you hear me?
Yep. Yes, I can hear you.
Okay, well, I typed in a few questions. I was not sure that I had to raise my hands also. I just wanted to ask you about the scripting software or the scripts that you used. I'm actually interested in this procedure, automating the whole optimization process. So I'd like to, if you give us some more details about this. That was very short.
Okay. Travis and/or Chris, do you want to take that one?
Yeah, I'll take this one. What kind of details are you looking for, Farouk? I mean, just you know, I mean, really, I guess maybe all I'm saying. So in the GUI interface that I was showing in point-wise, there was a series of parameters that was driving all that, and so maybe it's just best. Is the script still open, Darrell? Can you just flip over?
It should be. Yeah.
No, the actual. There we go.
Yeah.
So I mean, so Farouk, here's the script itself, and again, it's just, you know, Tickle is just a programming language. Now it's dynamic, where you don't actually have to compile the code; it's interpreted, and so it's just you know, storing all those variables that I either provide in the GUI, or in Travis's case where he ran it in batch. Those variables are populated with some sort of input, when in batch would have been through would have been driven by the output from the optimization algorithm, and so that's how it goes. And so, you know, based on some sort of equation here, so I'm showing the equation for the airfoils. I can go ahead and generate the points that govern the shape of the airfoil, and then based on that, I can create my mesh.
Right. Someone that, let's see, there's two questions. Again, this is for Travis. Did you take into two things? One, did you consider power generation as part of your simulation? Did you try to calculate the power output? And the second question, which is really a follow-on, did you look at optimizing other things such as blade angle of attack?
Okay. As far as the power output, no, it was a pure aerodynamic optimization. So just looking at the efficiency of the blades, no generator or anything of that sort. What was the next question, Drew?
The other question was around, did you consider trying to optimize the angle of attack as well?
Nope, I didn't try optimizing the angle of attack. I'm assuming he means the pitching of the blades about an axis of their own, because these blades experience different angles of attack as they rotate around the wind turbine. So they were just fixed in their relative positions.
Okay, cool. There's a couple of questions here, actually, about 3 of them around how did I make that nifty animation, and how hard and or easy was it to do. The animation capabilities in TechBot are pretty straightforward. Someone had asked to demo it. Basically, when you load in your results, if they are time aware, you get the VCR control. And frankly, it's as easy as, once you have the VCR control, moving through time is just a question of hitting play. So there's no magic here. It's actually quite simple. Again, if you're interested more in unsteady analysis, we will have a tutorial that will be coming in the early part of May, and so we'll go through that in detail. So I don't think it's worth going into great detail in terms of how one generates it outside of, say, it's a relatively straightforward operation. Let's see. Someone was asking about the actual code that you wrote for the optimization. What programming language did you use, Travis? Was it C, Python? What were you using?
Yeah, that was written in C.
C. Okay. We have time for perhaps one more question. So let's see. Looks like you have, let's see, how many divisions did you use along the blade length, and what is the length versus divided by the chord? What does that ratio look like? And I suspect that's either for Chris or Travis.
The number of divisions along the blade, I'm assuming that's how many points were along the blade. So to generate the blade, there were 1,000 points. In the mesh, not that many. Those are details that'll be in my paper, so he can talk to me a little bit offline about that.
Okay. So that was a short one, so we have time perhaps for one additional question. And we have Lou Wendy. Lou has actually raised his hand, or her hand, and so I'm going to go ahead and, Lou, you're on. If you have a question, you can go ahead and answer or ask that at this point. Okay, looks like she may have, or he may have already asked it via the question dialog. Okay, well, if there are no further questions, thank you again for spending the morning with us. Let me see if I can get back to the, so, okay. We're going to have an opportunity, if you have questions, again, please make sure that you either email them directly to support@pointwise or support at TechBot. We'll also have the transcripts of the questions that were asked and some answers to them available in the next few days for those people who didn't have an opportunity to catch all the questions. So with that, I wanted to, again, thank Chris and Travis from Pointwise for a very interesting discussion. Thank you, gentlemen. And thank all of you for joining us this afternoon. This recording will be available online perhaps by this afternoon. So if you want to go back to any part of this presentation, you're certainly able to do that via the recorded version of this webinar. Thank you again, and look forward to seeing you at the next event. Thank you.